For centuries, humanity gazed at the moon in awe, drawing inspiration, creating legends and seeking meaning in its luminous face. Yet, despite its familiar presence in the night sky, only half of the moon has ever been visible to earthbound observers. The other half, what we now call the far side of the moon, remained completely hidden until the advent of space exploration. This permanent invisibility is due to a phenomenon known as tidal locking, where the moon's rotational period perfectly matches its orbital period around the Earth. As a result, the same hemisphere of the moon always faces us, while the far side, cloaked in perpetual mystery, eluded our eyes for millennia. Unlike the near side, which features vast, dark volcanic plains known as Lunar Maria, the far side presents a dramatically different landscape. It is far more rugged, densely cratered, and notably lacks the large, smooth basaltic basins that define the near side. This asymmetry puzzled scientists for decades and gave rise to various speculations, both scientific and mythical. In ancient times, with no means to observe the hidden hemisphere, some cultures believed the far side might host fantastical creatures, lost civilizations, or even mirror worlds. These myths endured until the space age offered a glimpse beyond the moon's familiar face. The veil of mystery began to lift in 1959, when the Soviet Union's Lunar 3 mission became the first spacecraft to photograph the moon's far side. The grainy images it transmitted to Earth marked a turning point in lunar science. They revealed a surface pockmarked with craters, devoid of the wide maria that characterized the near side. Scientists were astonished at the stark contrast. The photographs provided evidence that the moon's two hemispheres had followed very different geological paths, prompting new hypotheses about the moon's formation and evolution. Lunar 3's mission, though short-lived, opened the door to a new realm of exploration, setting the stage for deeper investigations into the moon's structure, history, and potential for future missions. The reason for the stark differences between the near and far sides lie deep within the moon's internal dynamics. Research suggests that the crust on the far side is significantly thicker than that on the near side. This discrepancy in crust thickness may be rooted in the moon's early formation processes, particularly the uneven cooling of the lunar body after its formation. One prevailing theory posits that the Earth, in its early molten state, radiated immense heat toward the moon's near side, which faced it due to tidal locking. This heat may have prevented the near side from forming a thick crust, while the far side, shielded from Earth's radiation, cooled more quickly and developed a thicker, more solid outer shell. These thermal differences could explain why the near side experienced extensive volcanic activity, creating maria, while the far side remained rugged and cratered. Among the many fascinating features of the far side is the South Pole Aitken Basin, an enormous impact crater that stands as one of the oldest and largest in the entire solar system. Spanning approximately 2,500 kilometers in diameter and reaching depths of up to 13 kilometers, this colossal basin covers a vast expanse of the moon's southern hemisphere. Its formation dates back over 4 billion years, possibly resulting from a massive asteroid collision during the early bombardment period of the solar system. The South Pole Aitken Basin offers a unique window into the moon's deep crust, and possibly its upper mantle, as the impact likely excavated material from deep beneath the surface. By studying this region, scientists hope to uncover clues about the moon's early internal composition and the violent processes that shaped not only the moon, but the inner planets as well. The far side's scientific value extends beyond geology. Its location makes it an exceptional site for future astronomical observatories, particularly radio telescopes. Earth's atmosphere and constant electromagnetic noise from human technology interfere with sensitive radio observations. The far side of the moon, however, is permanently shielded from these disturbances by the moon's bulk. This natural radio silence zone presents an ideal environment for detecting faint cosmic signals from deep space, including emissions from the early universe, long before stars and galaxies formed. Placing radio telescopes on the far side could allow astronomers to study phenomena that are otherwise impossible to observe from Earth or Earth-orbiting satellites. In particular, such observatories could help scientists investigate the cosmic dark ages, providing insights into how the first stars and galaxies emerged from primordial hydrogen. Exploration of the far side remains a frontier largely untouched, but efforts are underway to change that. China made history in January 2019 with its Chang'e 4 mission, the first spacecraft to land on the Moon's far side. The mission delivered the Yutu-2 rover to the von Karman crater, located within the South Pole Aitken Basin. Because direct communication with Earth is impossible from the far side, China deployed a relay satellite, Huaqiao, positioned at the Earth-Moon L2 Lagrange point. This satellite enabled data transmission between the rover and mission control. The success of Chang'e 4 not only demonstrated the technical feasibility of far-side missions, but also underscored the immense scientific potential of this mysterious hemisphere. The mission's findings have already begun to reshape our understanding of lunar geology, with new data on surface composition, radiation levels, and the mechanical behavior of the lunar regolith. Beyond the scientific allure, the far side of the Moon holds strategic importance for space exploration and geopolitical interests. As nations and private enterprises ramp up lunar activity, the far side is emerging as a prime location for future missions and potential settlements. Its unexplored terrain offers a blank slate for deploying infrastructure, such as relay stations, resource extraction facilities, or scientific bases. Moreover, the far side's isolation from Earth's influence provides an environment suitable for testing technologies needed for long-duration space missions, including deep space navigation, autonomous systems, and sustainable life support. Establishing a foothold on the far side could pave the way for more ambitious ventures, such as crewed missions to Mars or even interplanetary communication relays. The Moon's far side may also contain deposits of valuable resources. Though no large-scale mining has yet occurred, lunar scientists have identified potential sources of rare Earth elements, water ice in permanently shadowed craters near the poles, and helium-3, a lightweight isotope that could be used in future fusion energy technologies. While these resources exist in unknown quantities, their presence further elevates the strategic and economic value of exploring the far side. Future missions will likely include detailed surveys and robotic excavations to assess the feasibility of resource utilization. Despite its promise, the far side also presents daunting challenges. Its rough terrain, communication blackout, and harsh environmental conditions make exploration more difficult than on the near side. Any mission to this region must overcome these obstacles through advanced engineering, autonomous navigation, and robust power systems capable of withstanding the 14 Earth-day-long lunar nights. Innovations such as nuclear-powered landers, AI-driven rovers, and modular-based designs will play a crucial role in future far-side operations. As technology evolves, so too does our capacity to unlock the secrets hidden in this enigmatic realm. The far side of the Moon represents a unique and largely untapped repository of knowledge. Its geological features tell the story of a different evolutionary path, one shaped by deeper crustal formation and fewer volcanic processes. From the massive South Pole Aitken Basin to the potential for cosmic radio silence, this hemisphere is more than a blank slate. It is a historical archive etched in rock and regolith. With growing international interest and rapid advancements in space technology, the far side may soon move from shadow to spotlight, revealing not only the Moon's deepest mysteries, but also pointing the way forward in humanity's journey beyond Earth. As the next era of lunar exploration begins, the far side stands ready to offer answers to questions we have only just begun to ask. The dawn of the space age was inseparable from the geopolitical tensions of the Cold War. At the center of this monumental rivalry between the United States and the Soviet Union stood not just Earth's orbit, but the Moon itself, especially the mysterious unseen far side. Until the late 1950s, no human eyes had glimpsed this hidden hemisphere. Its secrets were locked away by tidal locking, a gravitational phenomenon causing the Moon to rotate in perfect synchrony with its orbit around Earth, perpetually showing only one face. This left the far side a blank slate, both literally in our maps and metaphorically in our understanding. When the Soviet Union's Lunar 3 mission returned the first images of this enigmatic region in 1959, the geopolitical and scientific worlds were shaken. What was unveiled was a terrain unlike anything ever imagined, rugged, ancient, scarred by craters, and virtually devoid of the dark Maria plains that characterize the Moon's near side. These images didn't just transform our understanding of lunar geology, they ignited a new front in the already burning space race. Lunar 3's success was a symbolic and strategic triumph for the Soviet Union. At a time when space exploration was not only about science, but about demonstrating technological superiority and ideological dominance, the USSR's ability to photograph the far side of the Moon gave it a crucial psychological edge. It was a wake-up call for the West. The mission achieved what had previously been thought impossible. The spacecraft, using onboard film processing equipment and radio transmission, sent back images that were grainy but revolutionary. These images depicted a side of the Moon that was drastically different in appearance, filled with overlapping craters, jagged mountain ranges, and a noticeable absence of the broad basaltic plains visible on the side facing Earth. For Western scientists, the revelations posed a multitude of new questions. For politicians and military strategists, they raised an alarm. From a geopolitical perspective, the Moon, and especially its unseen half, quickly transformed from a mere scientific curiosity into a domain of strategic interest. If a nation could reach and explore the Moon, it demonstrated the capability to launch advanced rockets, satellites, and potentially nuclear weapons across intercontinental distances. As such, Lunar 3's success was not only about scientific discovery, it was perceived as a declaration of technological prowess and a veiled threat. The American response was swift and multifaceted, involving not just NASA, but also the US military and intelligence community. Agencies such as the CIA began exploring the implications of lunar exploration for national security, pondering whether the Soviet Union could utilize the Moon for surveillance, military infrastructure, or space-based weapons, ideas that would later become recurring themes in space strategy discussions. In response to Soviet advancements, the United States accelerated its own lunar reconnaissance efforts. The Lunar Orbiter program, launched between 1966 and 1967, played a crucial role in the systematic mapping of the Moon's surface. Unlike Lunar 3, which captured only a few dozen images of the far side, the American Lunar Orbiter missions were designed to photograph and map nearly the entire lunar surface, including both hemispheres in high resolution. These missions served dual purposes. Scientifically, they provided critical data for understanding lunar geology and identifying interesting sites for future exploration. Strategically, they were essential for mission planning, particularly for the Apollo program, which was then moving full steam ahead. Choosing suitable landing sites on the near side required detailed imaging to ensure the safety of astronauts and equipment. Moreover, in the event of an aborted Apollo mission or loss of control, knowing the terrain on the far side was vital for evaluating emergency landing options. The urgency behind these efforts was intensified by the militarization of space, a subject quietly but intensely explored by defense agencies on both sides of the Iron Curtain. The far side of the Moon, perpetually shielded from Earth-based observation and radio signals, seemed to offer a perfect hiding place for strategic installations, surveillance equipment, or even missile bases, though none of these were ever built. The CIA commissioned internal studies and satellite reconnaissance efforts to assess Soviet lunar activities and their implications for American security. Although most of these fears never materialized, They reflect how seriously the unknown territories of the Moon were taken by Cold War strategists. The competition to map the Moon was therefore not just about science or exploration, it was about asserting dominance in a new domain, outer space. As mapping capabilities improved, new technologies were introduced to further refine our understanding of the Moon's surface. While the initial Lunar Orbiter missions used photographic film developed in space and then scanned for transmission, later missions utilized digital imaging, radar mapping, and infrared sensors. Among the most significant missions in this regard was Clementine, a joint endeavor by the Department of Defense and NASA launched in 1994. Clementine employed a suite of advanced imaging technologies to conduct a comprehensive survey of the Moon, including the far side. Using multispectral imaging and laser altimetry, Clementine mapped the Moon's topography in unprecedented detail. It confirmed earlier observations that the far side is more mountainous, heavily cratered, and lacks the widespread volcanic plains of the near side. It also contributed to the discovery of possible water ice in permanently shadowed regions near the lunar poles, an insight that further increased the far side's importance for future exploration and potential habitation. Following Clementine, NASA launched the Lunar Reconnaissance Orbiter, LRO, in 2009, a mission that remains operational to this day. Equipped with high-resolution cameras and a powerful radar system, LRO has revolutionized our understanding of the lunar surface. Its data has created incredibly detailed maps of the Moon, allowing scientists to measure crater depths, assess surface roughness, and even detect subtle changes over time. These detailed maps revealed that the far side contains some of the oldest, most heavily bombarded regions of the Moon, making it a geological time capsule from the early solar system. The dense cratering on the far side suggests that it has undergone fewer resurfacing events than the near side, which was flooded with basaltic lava during a period of extensive volcanic activity. This insight has helped scientists reconstruct the Moon's evolutionary history, including the processes that differentiated its two hemispheres. The improved mapping of the far side also had critical implications for mission planning and engineering. Because of its rough terrain and lack of flat plains, landing a spacecraft safely on the far side is significantly more difficult than on the near side. Every potential landing site must be evaluated not only for scientific interest, but also for logistical feasibility, including slope, rock abundance, surface composition, and illumination cycles. In addition, because direct radio communication with Earth is impossible from the far side without a relay system, mapping efforts were essential in planning relay satellite placement and identifying suitable locations for surface operations. Missions like China's Chang'e 4, which successfully landed on the far side in 2019, benefited immensely from decades of American and international mapping data. That mission placed its lander in the von Karman crater within the South Pole Aitken Basin, a region identified as scientifically rich and geologically stable due to detailed reconnaissance from past missions. As the 20th century gave way to the 21st, the motivation behind lunar mapping shifted from Cold War rivalry to international collaboration and commercial potential. But the legacy of Cold War exploration is deeply embedded in every modern lunar mission. The early Soviet and American efforts to map the Moon, driven by a mix of curiosity, competition, and fear, laid the groundwork for everything that followed. Without the images from Luna 3, the detailed surveys from the Lunar Orbiter program, and the military-funded data from Clementine, humanity would still be in the dark about half of the Moon's face. These programs turned the far side from a blank slate into a richly detailed landscape, filled with geological complexity and scientific promise. Today, the far side remains a focal point for lunar science, not because of Cold War tensions, but because of its potential to answer fundamental questions about the early history of the solar system. It contains ancient rocks that may predate much of the Earth's surface, offering a glimpse into the chaotic period when planets were still forming. The far side's crustal thickness, crater density, and unique composition provide a contrast that helps scientists test models of planetary differentiation, heat flow, and impact dynamics. In short, the far side serves as a natural laboratory for understanding planetary evolution on both small and large scales. Despite all the technological progress, many mysteries still remain. The mapping of the Moon, while vastly improved, is not yet complete at the granular level needed for large-scale operations, construction, or resource extraction. Scientists continue to refine digital elevation models, mineralogical maps, and thermal profiles using data from LRO and other international missions. Future mapping efforts will likely involve low-orbit constellations, robotic landers, and in-situ sensors to provide three-dimensional, real-time data, essential for the next generation of lunar activities, whether scientific, commercial, or exploratory. The far side of the Moon began its modern journey from myth to mapped reality during one of humanity's most intense political rivalries. What started as a race to demonstrate supremacy in space became a mission to understand a celestial body that had always hovered above us, yet remained half-shrouded in mystery. The competition between the US and the Soviet Union pushed the boundaries of what was technologically possible, forcing each side to explore, map, and understand the unknown faster than they might have otherwise attempted. As a result, the far side of the Moon, once the great unseen, is now a deeply studied, scientifically significant landscape. But even today, it continues to challenge us with its rugged terrain, complex geology, and potential to reshape our understanding of the Moon, the Earth, and the broader universe. The Apollo program remains one of the most ambitious and celebrated efforts in the history of human exploration. It was a project that began as a political goal in the heat of the Cold War, but evolved into a scientific and technological milestone for all of humanity. The primary focus of the Apollo program was to land humans on the Moon and return them safely to Earth. And while it succeeded in that goal with 6 crewed lunar landings between 1969 and 1972, all of these missions landed only on the Moon's near side, the hemisphere that permanently faces the Earth. The far side of the Moon, while a subject of great interest for scientists, remained untouched by human hands during the Apollo era, largely due to the formidable technical and logistical challenges it presented. The first and most critical reason the far side was never visited during the Apollo program was communication. The Moon is tidally locked to the Earth, which means one hemisphere, the near side, is always visible from Earth, while the far side is in permanent shadow from our planet's point of view. During the Apollo missions, constant two-way communication between mission control on Earth and the astronauts on the lunar surface was a non-negotiable requirement. This real-time contact was essential for navigation, monitoring life support systems, managing scientific experiments, and ensuring safety during emergencies. Had NASA attempted to land a crew on the far side of the Moon, the spacecraft would have been out of direct radio contact with Earth the entire time they were on the surface. This communication blackout posed an unacceptable risk at the time, particularly with the technology available in the late 1960s and early 1970s. There were no relay satellites in lunar orbit capable of bridging the communication gap, and without such infrastructure, a mission to the far side would have left astronauts entirely isolated, unable to call for help if something went wrong. Despite these limitations, the Apollo missions did gather important information about the far side through orbital passes and remote sensing. When Apollo spacecraft orbited the Moon, they traveled around the entire body, giving scientists a valuable opportunity to study both the near and far hemispheres from above. High-resolution cameras, spectrometers, magnetometers, and other instruments aboard the orbiting command and service modules collected data that helped map the topography, composition, and gravitational anomalies of the lunar surface. These orbital studies revealed that the far side was markedly different from the near side. It was more heavily cratered, had a thicker crust, and lacked the large maria, dark basaltic plains formed by ancient volcanic activity that dominate the near side. These differences sparked deep scientific curiosity and raised many questions about the Moon's geological history, internal structure, and the forces that shaped its two faces so differently. One of the most dramatic moments in the Apollo program involving the Moon's far side occurred during the Apollo 13 mission. Launched in April 1970, Apollo 13 was intended to be the third crewed mission to land on the Moon, but an onboard explosion crippled the spacecraft, forcing the crew to abort their landing and instead execute a perilous return trajectory using the Moon's gravity to slingshot them back toward Earth. As part of this trajectory, the Apollo 13 spacecraft looped around the far side of the Moon. For a tense period of approximately 25 minutes, mission control on Earth lost all contact with the crew as they passed behind the Moon, an expected blackout caused by the lack of line-of-sight communication. In those moments, the astronauts were alone, beyond the reach of Earth, with no ability to receive instructions or send distress signals. This incident underscored the significant risks associated with any mission to the far side and reinforced NASA's cautious approach. Until reliable satellite relays or autonomous onboard systems could ensure constant communication, sending humans to the Moon's hidden hemisphere remained out of the question. Throughout the Apollo program, the far side was never out of mind for scientists and mission planners. The command modules that remained in orbit around the Moon during surface operations collected telemetry and imaging data across both hemispheres. These efforts resulted in increasingly detailed lunar maps and an understanding of gravitational variations that could impact future missions. Tracking data from this orbiting spacecraft allowed scientists to study the Moon's gravitational field and to detect mass concentrations, known as mascons, that could subtly alter the trajectory of orbiting spacecraft. Some of these mascons were found on the far side, and understanding their effects became essential to planning safe orbits and future landings. The data also contributed to hypotheses about the Moon's internal structure, crustal composition, and possible asymmetrical formation due to early tidal heating or differences in solar exposure. Apollo 17, the final mission of the Apollo program, contributed particularly valuable scientific data relevant to the far side. While it too landed on the near side, it targeted the Taurus-Littrow Valley near the eastern limb of the Moon, a region that borders the far side and offers geological features similar to those found across the Moon's hidden hemisphere. The crew collected samples from highland terrain, which was more representative of the far side's crustal composition than the Maria regions explored in earlier missions. Instruments on the Apollo 17 service module gathered high-resolution ultraviolet and infrared data, helping scientists to better interpret the far side's geological structure and mineral distribution. These findings deepened humanity's understanding of the Moon as a whole and provided indirect but meaningful insight into the far side's history. Despite these advances, the reality remained that no crewed mission had ever set foot on the far side. The technological constraints of the time made such a feat impractical, and as the 1970s progressed, political and financial priorities shifted away from lunar exploration. NASA had originally planned additional Apollo missions beyond Apollo 17, including Apollo 18, 19, and 20, and there had been internal discussions about possibly using these later flights to explore more remote or scientifically valuable regions of the Moon, including the far side. However, escalating costs, waning public interest, and competing demands for government funding led to the cancellation of these missions. The remaining Saturn V rockets were either repurposed for other projects or displayed in museums, and the Apollo program came to an end. The absence of a crewed far-side landing did not mean the end of interest. Scientists continued to push for future missions that could target the far side, both robotic and eventually human. But the necessary infrastructure, such as relay satellites in lunar orbit or autonomous rovers capable of conducting science and communicating through alternative means, would not be realized until decades later. In the meantime, the Apollo program's legacy was cemented not just in the historic footsteps left on the Moon's surface, but in the rich trove of data and experience it provided. This knowledge would prove indispensable as new nations entered the space arena and as NASA and its partners began planning more ambitious return missions under programs like Artemis. In retrospect, the Apollo missions can be seen as both a remarkable achievement and a missed opportunity. While the 6 crewed landings fundamentally changed humanity's relationship with the Moon and brought back hundreds of kilograms of lunar material, the decision to limit landings to the near side constrained the scope of scientific exploration. The far side remained a scientific frontier, one that could offer answers to some of the most profound questions about planetary formation, solar system evolution, and even the origins of life. The thick crust, the lack of volcanic plains, and the deep impact basins on the far side contain clues that could rewrite parts of our understanding of lunar history. As the 21st century progresses, the groundwork laid by Apollo becomes increasingly relevant. New missions, such as those led by China, have touched down on the Moon's far side, demonstrating what was once impossible. NASA and its international partners now have the benefit of decades of technological advancement, from satellite relays and high-bandwidth communications to autonomous systems and advanced propulsion. These tools open the door for humans to one day return to the Moon, not just to repeat the triumphs of Apollo, but to go further, to explore the far side, to set up scientific observatories shielded from Earth's noise, to mine ancient impact sites for clues about the solar system, and to establish a permanent human presence that spans both hemispheres. The Apollo program's limited reach was not a failure, but a necessary stepping stone. The choice to focus on the near side was guided by logic, safety, and feasibility, not lack of vision. The data it returned included the seeds of far-side exploration, and its lessons continue to shape mission design to this day. The far side of the Moon still awaits the first human footprint, and when that moment comes, it will owe much to the brave astronauts, engineers, and scientists of the Apollo era who dared to look beyond Earth and who prepared humanity for the even greater steps to come. In the history of lunar exploration, the year 2019 marked a profound turning point that reshaped global perceptions of space leadership. For decades, the Moon had been visited, mapped, orbited, and explored, yet always from the near side, the hemisphere that perpetually faces Earth due to tidal locking. The far side, by contrast, remained a realm of mystery, perpetually hidden from view and technologically difficult to access. Then came China's bold step, the Chang'e 4 mission, a moment of quiet but undeniable significance in the annals of space history. With this mission, China not only became the first nation to soft land a spacecraft on the far side of the Moon, but also staked its claim in a new era of scientific exploration and strategic space competition. Chang'e 4 launched on December 7, 2018, atop a Long March 3B rocket from the Xicheng Satellite Launch Center in China's Sichuan province. This mission was part of China's wider Chang'e program, named after the moon goddess in Chinese mythology. While the earlier Chang'e missions had orbited or landed on the Moon's near side, Chang'e 4 was explicitly designed to do what no nation had done before: reach and study the far side. This feat was not just about national pride or symbolic leadership. Scientifically, the far side of the Moon offers a relatively pristine environment for studying the early solar system, free from the electromagnetic interference of Earth. Strategically, landing and operating on the far side demonstrates high levels of technological self-reliance and precision. One of the most critical challenges in executing this mission was the communication barrier. Since the far side of the Moon is perpetually turned away from Earth, direct radio communication with a lander or rover would be impossible. To solve this, China launched a dedicated relay satellite named Huaqiao in May 2018. Positioned in a halo orbit around the Earth-Moon, L2 Lagrange point, roughly 65,000 kilometers beyond the Moon, Huaqiao served as a communications bridge between the lander on the Moon's far side and mission controllers back on Earth. This innovative use of orbital mechanics and satellite positioning was key to the mission's success and has become a template for future far-side operations, whether by China or other nations. On January 3, 2019, the Chang'e 4 lander successfully touched down within the von Karman crater, a 186-kilometer-wide depression located in the southern hemisphere of the far side, inside the much larger South Pole Aitken Basin. This basin is one of the oldest and deepest impact structures in the solar system, believed to have been formed over 4 billion years ago. It represents an invaluable site for planetary scientists hoping to understand the Moon's interior structure, its geologic history, and by extension, clues about the early Earth. The selection of this specific site was strategic, not only for its scientific richness, but also for its relatively stable terrain that allowed safe landing and rover deployment. The lander deployed the Yutu-2 rover, a successor to the earlier Yutu, Jade Rabbit rover, used in the Chang'e 3 mission. Yutu-2 began its exploration with a series of short-distance drives and observations. Equipped with ground-penetrating radar, panoramic cameras and spectrometers, the rover began transmitting an abundance of data about the lunar surface. One of its first surprises was the discovery of a mysterious gel-like substance within a small crater. While later analysis suggested that the substance was likely a form of melted lunar rock, possibly created by the intense heat of a meteor impact, the find nonetheless captured global attention and highlighted the unexpected nature of real-time exploration on the far side. The radar system on board Yutu-2 provided scientists with unprecedented data about the subsurface structure of the Moon's far side. Unlike earlier missions, which offered limited surface-level observations, Chang'e 4 gave researchers a multi-layered view of the Moon's geological history. Radar imaging revealed at least 3 distinct layers of materials beneath the surface, suggesting a complex evolution that included ancient lava flows, ejecta from distant impacts, and regolith buildup. These findings help refine models of how the Moon's crust formed and evolved over billions of years, and offer comparative data for studying other rocky celestial bodies. In addition to its geological objectives, Chang'e 4 carried several scientific experiments. Among the most notable was a biological experiment designed to test whether life could be sustained on the lunar surface. A small biosphere container housed seeds of cotton, potato, and Arabidopsis, a flowering plant, as well as yeast and fruit fly eggs. Shortly after landing, Mission Control reported that one of the cotton seeds had sprouted, marking the first time a plant had germinated on the Moon. Though the experiment was short-lived due to temperature fluctuations, it represented a significant step in understanding the feasibility of future long-term lunar habitats and sustainable life support systems. Chang'e 4's success also demonstrated China's growing sophistication in spaceflight engineering. Precision landing technology, autonomous navigation, and long-distance communication capabilities all had to be developed and flawlessly integrated. Each subsystem, whether the lander, the rover, or the relay satellite, had to perform perfectly in coordination. This achievement sent a powerful message to the international space community. China was not merely catching up, it was now setting precedents. While the US, Russia, and European nations had historically dominated lunar exploration, China's bold move into uncharted territory redefined the balance of space power and ambition. The mission's geopolitical implications were equally significant. By pioneering far-side exploration, China effectively opened a new arena of lunar activity that had previously been avoided due to technical and logistical limitations. The mission rekindled interest among other nations and private entities in the scientific and commercial potential of the Moon's far side. Ideas for constructing radio astronomy observatories, establishing research bases, or testing new technologies in isolated lunar environments have since gained traction. These developments, in part catalyzed by Chang'e 4, signal the emergence of a multipolar space age where new players like China take bold initiatives and establish footholds in areas long considered too difficult or dangerous. Moreover, Chang'e 4 laid the groundwork for China's future lunar ambitions. The follow-up mission, Chang'e 5, which launched in late 2020, focused on sample return from the Moon's near side. Plans for Chang'e 6, 7 and 8 include proposals for exploring the South Pole, establishing robotic infrastructure, and ultimately supporting crewed landings. Chang'e 4 is not just an isolated triumph but part of a deliberate sequential effort to build long-term lunar capability. With these missions, China is not only exploring but laying the foundation for permanent infrastructure that could serve both scientific and strategic purposes. In the broader context of human exploration, Chang'e 4 represents the kind of high-risk, high-reward mission that drives innovation and reshapes scientific frontiers. The Moon's far side had long remained unexplored due to the sheer complexity involved. China's success in overcoming these obstacles opens the door to new possibilities, not just for robotic missions, but eventually for human presence. Discussions about lunar bases, in-situ resource utilization, and interplanetary staging points all benefit from the insights gained through Chang'e 4. Chang'e 4 mission was a landmark event that changed how the world views both the Moon and China's role in space. It demonstrated that the far side is no longer beyond reach, that national ingenuity can conquer technical hurdles, and that bold exploration can yield profound scientific and strategic rewards. Through this mission, China transformed what had long been a scientific curiosity into a practical frontier for discovery. The Moon's far side, once silent and remote, now speaks through the instruments and wheels of Chang'e 4, ushering in a new chapter in humanity's journey beyond Earth. The far side of the Moon, long obscured from direct observation and only recently accessed through advanced space missions, stands as a geological archive of immense value. Unlike the near side that has been subject to repeated exploration, imaging, and even sample returns, the far side has remained largely untouched and unaltered, offering a more pristine glimpse into the Moon's earliest epochs. As scientists delve deeper into its surface features and underlying structures, they are uncovering secrets that not only illuminate the Moon's own complex evolution, but also provide key insights into the broader history of the solar system. One of the most significant revelations from far-side exploration is the stark contrast in crustal composition and geological history when compared to the Moon's near side. Analysis of high-resolution imagery and sensor data has revealed that the far side features older, thicker crust and bears the marks of deeper, more extensive impact scars. These scars are the result of ancient bombardments from asteroids and other celestial bodies during the chaotic early days of the solar system. Unlike the near side, which shows significant signs of lava flooding and volcanic resurfacing, the far side has remained relatively stable, preserving features that date back nearly 4.5 billion years. At the heart of these geological studies is the South Pole Aitken Basin, the largest and one of the oldest known impact structures on the Moon, measuring roughly 2,500 kilometers in diameter and up to 8 kilometers deep. Located in the Moon's southern hemisphere on the far side, this immense basin is a treasure trove of geological data. Scientists believe that the impact event that created this basin was powerful enough to punch through the lunar crust and expose materials from the lower crust or even the mantle. If confirmed, this would make the South Pole Aitken Basin one of the few locations in the solar system where scientists can study subsurface planetary layers without the need for deep drilling. Investigations into the surface composition of this region have revealed a high concentration of anorthosite, a light-colored igneous rock that is believed to have formed during the Moon's early crustal differentiation. Anorthosite is typically associated with the lunar highlands and is thought to be one of the first types of rock to solidify from the Moon's primordial magma ocean. Its widespread presence on the far side, particularly in elevated regions, points to an ancient, unaltered crust that has endured since the Moon's formation. This is in stark contrast to the near side, where volcanic activity has covered large areas with darker basaltic lava flows. This lack of basalt on the far side has puzzled scientists and led to intriguing theories about the Moon's internal thermal dynamics. One explanation lies in the phenomenon of uneven tidal heating. During the early formation of the Earth-Moon system, gravitational interactions between the two bodies generated tidal forces that may have caused asymmetrical heating within the Moon's interior. This localized heating on the near side could have led to more volcanic activity and magma generation, while the far side remained cooler and geologically quieter. This theory is supported by the absence of large maria, vast basaltic plains, on the far side, which are prominent features of the near side. The far side's preserved landscape also serves as a natural archive of impact history. Crater density studies suggest that this region was heavily bombarded during a period known as the Late Heavy Bombardment, roughly 4 billion years ago. During this era, the inner solar system experienced a spike in collisions with asteroids and other space debris. Because the far side has experienced minimal volcanic resurfacing since that time, it retains a high concentration of craters that provide critical evidence of the intensity and distribution of these ancient impacts. By studying these craters' size, distribution, and degradation patterns, scientists are able to reconstruct the chronology of lunar and, by extension, solar system evolution. Moreover, the regolith on the far side holds potential answers to some of the most fundamental questions about cosmic history. Isotope analysis of the lunar soil can reveal information about the types and sources of solar radiation that have bombarded the Moon over billions of years. Some isotopic signatures may even hint at galactic events such as nearby supernova that left a chemical imprint on the lunar surface. Unlike Earth, which has an atmosphere and magnetic field that shield and alter incoming cosmic particles, the Moon lacks such protective barriers. As a result, it records solar and galactic radiation directly into its surface materials, acting as a kind of cosmic data recorder. Adding to the intrigue is the detection of thorium and other rare Earth elements in specific regions of the far side. These elements are typically associated with volcanic processes and suggest that despite its overall geological calm, the far side may have experienced localized volcanic activity in the distant past. These pockets of ancient volcanism raise questions about the Moon's internal heterogeneity and whether different parts of its mantle possessed varying chemical compositions that could have influenced surface features. The presence of thorium is particularly notable because it is radioactive and could have contributed to localized heating, potentially altering the thermal balance of the crust in those regions. The geological richness of the far side has led many experts to describe it as a natural time capsule. Unlike Earth, where plate tectonics, weather, and biological activity continuously recycle and alter the surface, the Moon's far side has been largely inert and unchanging. This makes it an ideal location for preserving evidence of primordial events. The terrain there offers a direct window into the conditions and processes that dominated the early solar system, including the mechanics of planetary formation, crust differentiation, and impact-driven evolution. The importance of the far side has only grown with the data returned by recent missions such as China's Chang'e 4. With its ground-penetrating radar and spectrometers, the U-22 rover has added empirical depth to previous orbital observations. It has helped map the subsurface layers, revealing a complex stratigraphy of ancient lava flows, ejecta blankets, and regolith buildup. These findings underscore the Moon's geological diversity and challenge long-standing assumptions about its formation and development. For instance, the discovery of layered structures suggests that the far side may have undergone episodic volcanic activity long after its crust initially solidified. These discoveries are not merely academic. They have direct implications for future lunar missions, especially those aimed at establishing permanent scientific or even commercial installations. Understanding the geological stability, resource availability, and radiation exposure levels on the far side is essential for designing infrastructure that can endure the harsh lunar environment. Elements like thorium and rare earths could one day be harvested for high-tech applications, while the anorthosite crust could serve as a raw material for construction. But perhaps more importantly, the far side's geological record could serve as a foundational dataset for comparative planetology, helping scientists draw parallels and distinctions between Earth, the Moon, Mars, and other rocky bodies. The far side of the Moon is a geological frontier brimming with untapped potential. Its ancient crust, preserved impact history, and unique compositional features make it a scientific goldmine for understanding the Moon's early evolution and the broader dynamics of the inner solar system. As more missions target this enigmatic hemisphere, each layer of regolith and each crater examined brings us closer to unraveling the Moon's deepest secrets. The far side is not merely a destination, it is a key to unlocking the past, a silent witness to cosmic events that shaped not only our closest celestial neighbor, but the very planet we call home. As humanity stands on the edge of a new era of space exploration, the far side of the Moon has emerged as a focal point of strategic interest for scientific institutions, space agencies, and geopolitical powers alike. While traditionally overshadowed by the more familiar near side, which faces Earth and has been the site of every manned landing to date, the far side offers unique opportunities that are impossible to replicate anywhere else on the Moon or even on Earth. From radio astronomy and deep space communications to defense applications and potential lunar colonization, the strategic potential of the lunar far side extends far beyond its surface features. One of the most compelling arguments for establishing a permanent scientific or operational presence on the Moon's far side is its natural shielding from Earth's electromagnetic interference. The Moon is tidally locked, meaning the same side always faces Earth, while the opposite side, the far side, remains permanently turned away. This configuration effectively blocks all Earth-originating radio frequency noise, making the far side a pristine and extraordinarily quiet environment for conducting sensitive radio astronomical observations. The potential here is nothing short of revolutionary. Scientists envision deploying large, low-frequency radio telescopes in this quiet zone, which could allow humanity to detect faint signals from the early universe that are currently drowned out by Earth's constant electromagnetic chatter. Of particular interest are signals from the cosmic dark ages, the epoch following the Big Bang and preceding the formation of the first stars. This period remains one of the least understood chapters in cosmology, mainly because its low-frequency radio emissions are virtually impossible to detect from Earth due to atmospheric distortion and technological interference. A lunar far-side observatory would be uniquely positioned to capture these signals. It could help scientists learn how matter cooled, how the first atoms and molecules formed, and how the earliest cosmic structures began to emerge. Such discoveries could fundamentally alter our understanding of the universe's origin, structure, and fate. Beyond pure science, the far side of the Moon holds enormous potential as a hub for space communications. As exploration efforts push deeper into the solar system, the need for reliable communication relays and data transmission networks becomes critical. Placing relay satellites or surface-based communication arrays on the far side could dramatically enhance contact with distant spacecraft, especially those operating in blind spots relative to Earth-based stations. These facilities could serve as vital nodes in a redundant space-based internet or backup network that ensures continuous operations even in the event of technical failures or hostile disruptions on Earth. The concept is already being put into practice. China's Chang'e 4 mission, the first spacecraft to land on the Moon's far side, was only made possible by deploying the Huaqiao relay satellite in a halo orbit around the Earth-Moon L2 Lagrange point. This satellite acts as a bridge between the far side and ground control, enabling constant communication despite the Moon's bulk obstructing direct radio contact. Future missions, including NASA's Artemis program, may adopt similar models, placing more relay systems in strategic positions to support extended crewed or robotic operations on the far side. This communications capability opens doors not only for scientific endeavors, but also for defense and strategic operations. The Moon, once considered a symbolic frontier, is increasingly being viewed through the lens of national security. Space agencies and defense departments in multiple countries have expressed interest in the Moon's far side for applications ranging from satellite tracking and surveillance to the development and potential testing of anti-satellite technologies. The Moon's vantage point offers a unique perspective for monitoring Earth-orbiting satellites in geostationary and other distant orbits. From the far side, specialized equipment could track movements, detect anomalies, and even intercept communications of spacecraft that may not be visible from Earth. The Moon's far side is also being evaluated for its suitability as a platform for deep space surveillance. Its unobstructed view of the outer solar system makes it ideal for detecting incoming comets, asteroids, or any spacecraft entering from deep space. This would complement existing Earth-based systems and enhance early warning capabilities. In this context, control over the far side could become a strategic asset in future conflicts or as part of broader national defense infrastructures. In terms of physical environment, the rugged and heavily cratered terrain of the far side may initially seem like a hindrance to settlement, but it actually offers some distinct advantages. For one, the terrain's natural topography provides a degree of protection against micrometeoroid impacts and cosmic radiation, both of which are significant hazards for long-term lunar habitation. Craters, caves, and lava tubes could be repurposed into shelters with minimal structural reinforcement, drastically reducing the resources required to construct safe living quarters. These natural features could also serve as laboratories for studying lunar geology or as storage sites for sensitive equipment and materials. The idea of underground habitats in particular is gaining traction. Lunar lava tubes, subsurface tunnels formed by ancient volcanic activity, have been detected on both sides of the Moon, but are believed to be more abundant and better preserved on the far side due to its lower levels of surface disturbance. These tubes could offer stable thermal conditions and physical shielding, making them ideal for supporting future lunar bases. Habitat modules could be deployed inside these tunnels to minimize the effects of solar flares, cosmic rays, and extreme temperature fluctuations, which vary from blistering heat during the lunar day to freezing cold at night. NASA's Artemis program and other international lunar missions have increasingly acknowledged the importance of exploring and possibly utilizing the Moon's far side. Relay satellites and advanced surface navigation systems would be key enablers for such ventures. As these programs mature, missions are expected to target regions on the far side not just for exploration, but for infrastructure development. This includes power generation through solar arrays, in-situ resource utilization, ISRU systems to extract water ice or minerals, and the establishment of long-duration crew habitats. Another dimension to the far side's strategic significance is its potential to become a flashpoint in the emerging contest over lunar territory. While the 1967 Outer Space Treaty prohibits the claiming of celestial bodies by any one nation, the increasing number of lunar missions and the lack of specific regulatory frameworks for territory management have led to a de facto race for presence and influence. Nations that establish permanent or semi-permanent infrastructure on the far side could effectively lay the groundwork for future geopolitical claims, or at least secure strategic advantages in science, defense, and commerce. Already, countries such as China, Russia, the United States, and members of the European Union are drafting blueprints for lunar stations, resource mapping expeditions, and industrial-scale operations. The far side, with its relatively unexplored terrain, is often cited in mission plans as an area ripe for pioneering efforts. Establishing a foothold there would not only symbolize a nation's technological prowess, but could also send a strong message about its spacefaring ambitions and capabilities. In the future, it's not inconceivable that long-term occupation or the deployment of key infrastructure on the far side will be seen as a marker of lunar dominance. Long-term infrastructure on the far side would not only serve near-term lunar goals, but could also act as a springboard for deeper space missions. Lunar bases could act as fuel depots, resupply stations, or assembly points for spacecraft destined for Mars, asteroids, or other deep space targets. Launching missions from the Moon requires significantly less energy than from Earth due to the lower gravitational pull, making it a cost-effective staging area for interplanetary travel. Crewed missions to Mars, in particular, would benefit from such support infrastructure, as they would need robust communication, supply, and emergency systems in place. Moreover, the presence of a human or robotic outpost on the far side would provide invaluable operational experience for managing long-duration missions in isolated environments. It would allow mission planners to refine life support systems, habitat design, and psychological protocols in preparation for the challenges of Mars or beyond. The far side would effectively serve as a proving ground for interplanetary colonization strategies, underlining its long-term strategic significance in the broader vision of human space expansion. The strategic importance of the Moon's far side lies at the intersection of scientific potential, communications infrastructure, defense capabilities, and geopolitical influence. Its isolation offers an unparalleled environment for radio astronomy and cosmic exploration, while its physical terrain supports ambitions for underground habitats and resource extraction. The ability to host communication relays and surveillance systems could redefine how space agencies interact with deep space missions and monitor Earth's orbital environment. As international interest intensifies and technological barriers fall, the far side is poised to become one of the most contested and valuable pieces of extraterrestrial real estate. The next few decades will likely see this silent hemisphere transformed from a mysterious backdrop into the center stage of humanity's next giant leap. Exploring the far side of the Moon presents a unique set of challenges that have long delayed direct access to this remote lunar region. Unlike the near side, which is constantly facing the Earth due to tidal locking, the far side remains in perpetual radio silence from ground control on Earth. This simple reality introduces a cascade of technological demands, logistical complexities, and innovative solutions that are reshaping how nations and agencies approach space exploration beyond Earth's line of sight. In recent years, advances in communication, power generation, artificial intelligence, and autonomous navigation have started to overcome some of the barriers that once made the far side virtually inaccessible. Yet it remains a harsh and unforgiving environment where every mission must be meticulously designed to account for communication limitations, extreme temperature swings, hazardous terrain, and the absence of existing infrastructure. The primary technological hurdle in exploring the far side stems from its permanent communication blackout. Because the Moon is tidally locked, the far side never rotates into Earth's view. This means that traditional line-of-sight radio signals from Earth cannot reach spacecraft or astronauts operating on that hemisphere. Without direct communication, real-time control, data transmission, and even basic telemetry become impossible. To solve this, relay satellites must be placed in specific orbits or strategic gravitational locations, such as the Earth-Moon Lagrange points. The most notable example is China's Huaqiao relay satellite, which was launched prior to the Chang'e 4 mission and positioned at the Earth-Moon L2 point. This location enables it to maintain continuous line of sight with both Earth and the Moon's far side, acting as a critical communication bridge. The success of Huaqiao has not only made Chang'e 4 operations possible, but also provided a model that other space agencies are now looking to replicate for their own future missions to the far side. Beyond communication, thermal regulation is another major challenge. The lunar day-night cycle lasts approximately 29.5 Earth days, which means that any mission on the Moon must endure 14 Earth days of blistering sunlight, followed by 14 Earth days of darkness and freezing cold. During the lunar night, temperatures can plummet to as low as -170 degrees Celsius, while daytime temperatures can soar to over 120 degrees Celsius. These extremes can damage electronic systems, degrade battery performance, and make long-term operation difficult. Innovations in thermal control include the use of multi-layer insulation, active thermal radiators, and heaters designed to keep critical systems within operational ranges. However, these solutions come at a cost in terms of energy demand and complexity. Spacecraft must either store enough energy during the day to survive the night, or be equipped with systems like radioisotope thermoelectric generators, RTGs, which provide continuous power regardless of sunlight. RTGs have been used successfully in many deep space missions, but raise safety, political and engineering concerns due to their use of radioactive materials. Power supply in general remains a critical issue for far-side missions. Solar panels are less effective during the long lunar night, and the lack of atmosphere means that energy storage systems must be extremely efficient and durable. During the Chang'e 4 mission, China combined solar arrays with robust battery systems to extend operational time for both the lander and the U-22 rover. For future missions, especially those that aim to establish a long-term presence or support human crews, hybrid power systems may be needed. These might include a combination of solar power, RTGs, and even experimental nuclear reactors. NASA has been developing compact fission reactors under the Kilo Power Project, which could one day supply sustained power to lunar bases, including those on the far side. Another challenge lies in the terrain of the far side itself. Unlike the near side, which features large, relatively flat volcanic plains known as maria, the far side is rugged, mountainous and heavily cratered. This landscape makes navigation, landing and mobility far more difficult. Rovers and landers must be equipped with advanced terrain mapping capabilities and hazard detection systems to avoid tipping over, becoming trapped, or colliding with unseen obstacles. High-resolution lunar maps generated by missions such as NASA's Lunar Reconnaissance Orbiter are helping planners identify safer landing zones and potential travel routes. Still, these maps cannot capture dynamic surface conditions like loose regolith, hidden sinkholes or sharp boulders. Therefore, real-time hazard detection using LiDAR, stereo imaging and ground-penetrating radar is becoming standard on robotic explorers. To navigate autonomously in such a hostile environment, rovers need to be equipped with sophisticated artificial intelligence, AI, and autonomous decision-making algorithms. Given the delay in communication caused by the relay satellite configuration and occasional signal loss, real-time remote control from Earth is often impossible. Rovers must be able to assess terrain, plan routes, detect hazards, and make decisions without waiting for instructions. The U-22 rover, part of the Chang'e 4 mission, demonstrated this to a limited extent by autonomously navigating around rocks and selecting interesting geological features for further study. Future generations of lunar rovers will need even more advanced onboard computing to carry out scientific analysis, execute sample collection, and manage energy consumption without human input. Dust management is another serious issue often underestimated. The moon's surface is covered in fine, abrasive regolith that clings to everything due to electrostatic charging. This dust can interfere with mechanical joints, obscure cameras and sensors, degrade solar panels, and pose health risks to human astronauts if inhaled or ingested. During the Apollo missions, astronauts reported persistent issues with lunar dust, contaminating their suits, equipment, and even the interior of their spacecraft. On the far side, where rescue or resupply would be even more difficult, keeping equipment clean and functional is a life or death matter. New materials, dust-repellent coatings, magnetic deflection systems, and electrostatic cleaning devices are being tested to address this problem. Returning samples from the moon has always been a significant technological and scientific challenge, but when the mission involves the far side of the moon, that challenge becomes exponentially more complex. The main hurdle lies in the absence of a direct line of sight between the moon's far side and Earth, which prevents straightforward communication between ground control and the spacecraft. This makes real-time monitoring, guidance, and troubleshooting nearly impossible without the help of a dedicated relay system. Consequently, robotic sample return missions on the far side require advanced levels of autonomy, sophisticated communication infrastructure, and precise mission design to ensure a successful round trip. One of the most ambitious upcoming missions that seeks to achieve this daunting task is China's Chang'e 6 mission. Following the success of Chang'e 4, the first spacecraft to land on the Moon's far side, Chang'e 6 aims to go a step further by landing on that same hemisphere, collecting physical samples and returning them to Earth. This would mark the first time in history that lunar material from the Moon's far side is brought back to our planet for direct study, potentially rewriting our understanding of the Moon's geological evolution. To appreciate the complexity of such a mission, it's essential to understand the major limitations and risks involved. In traditional sample return missions, communication plays a vital role at every stage, from descent, landing, and sample collection to launch from the lunar surface and eventual return to Earth. On the near side of the Moon, where missions like Apollo and Chang'e 5 have operated, continuous communication with Earth is relatively simple because the lander and orbiters can maintain direct contact with ground control. Engineers and scientists can send and receive real-time commands, adjust plans as needed, and respond to emerging problems with minimal delay. However, the Moon's far side is in perpetual radio silence from Earth due to the Moon's tidal locking. Since the same side of the Moon always faces Earth, the far side never does. As a result, any mission operating on that side is effectively blind and deaf to Earth unless a dedicated relay satellite is put in place. That's why China's deployment of the Huaqiao satellite before Chang'e 4 was such a groundbreaking step. Positioned at the Earth-Moon L2 Lagrange point, a gravitationally stable location, Huaqiao has a line of sight to both the Moon's far side and Earth, enabling consistent communication relays. For Chang'e 6, Huaqiao, or a follow-up relay system, will be essential to transmitting data and commands during every critical phase of the mission. But even with a relay satellite, communication is still limited by time delays and narrow bandwidth, meaning that real-time adjustments are minimal. Thus, Chang'e 6 and other far-side missions must include a high degree of onboard autonomy. The spacecraft will need to perform many key functions without Earth's immediate input. This includes landing procedures, sample collection, preparation for ascent, launch into lunar orbit, and rendezvous with the return module. Each of these stages is vulnerable to failure and leaves very little margin for error. The sample collection itself involves various subsystems that must work in sequence. Robotic arms or drilling mechanisms must identify and gather scientifically valuable material from the lunar surface. The samples are then sealed in a return capsule designed to survive the harsh vacuum and radiation of space. In Chang'e 5, this process was performed on the Moon's near side with help from real-time support from mission control. On the far side, all these steps must be pre-programmed and executed without intervention, increasing the stakes considerably. After the sample is secured, the ascent module must launch from the lunar surface and dock with an orbiter that will then return the capsule to Earth. This requires precise timing and navigational accuracy, all under autonomous control or with limited delayed command input via the relay satellite. Docking in lunar orbit is already a high-risk maneuver, and doing it without live control or visual confirmation compounds that risk. If Chang'e 6 successfully returns samples from the far side, the scientific rewards could be immense. One of its target areas is the South Pole Aitken Basin, the oldest, deepest impact structure on the Moon and one of the largest in the entire solar system. Because of its immense size and depth, scientists believe this basin may expose material from the Moon's lower crust or even its upper mantle, layers that are otherwise inaccessible. Studying these samples directly on Earth would allow researchers to better understand the Moon's internal composition, thermal evolution, and history of cosmic impacts. Moreover, lunar rocks from the far side are expected to differ significantly from those previously collected. Unlike the near side, which is covered in dark basaltic plains formed from volcanic activity, the far side features a thicker crust dominated by an orthosite, a light-colored ancient rock that formed early in the Moon's history. These geological differences may provide clues about the asymmetry between the Moon's two hemispheres and offer new insights into how celestial bodies differentiate and evolve over billions of years. Chang'e 6's success would also validate China's technical capability in conducting complex autonomous operations beyond Earth's direct reach. This would set the stage for more ambitious missions, not just on the Moon, but in other parts of the solar system where real-time communication is impossible. For example, Mars sample return missions face similar challenges, albeit on a grander scale. Lessons learned from Chang'e 6's relay, autonomy and navigation systems could feed directly into next-generation interplanetary missions. Beyond the scientific and technical implications, Chang'e 6 also carries geopolitical significance. It reinforces China's growing role as a leader in space exploration. While NASA and other space agencies have long dominated lunar science, China's success in landing on, exploring and potentially returning from the far side sets a new precedent. It demonstrates not only ambition but also a mastery of sophisticated mission planning, autonomous engineering and deep space communication strategies. This might further accelerate the global competition for lunar exploration, with the far side becoming a focal point for both scientific discovery and strategic infrastructure. As interest in crewed missions grows, the stakes get higher. Human survival on the far side would demand even more robust solutions. Habitats must be shielded from cosmic radiation, micrometeoroid impacts, and extreme temperatures. Engineers are exploring the possibility of constructing habitats in natural features like lava tubes, which are believed to exist beneath the lunar surface and may offer natural protection. Alternatively, inflatable or 3D printed structures using local materials such as regolith could reduce launch mass and enhance sustainability. Life support systems would need to be fully self-contained, recycling air, water and waste in closed-loop environments. Emergency evacuation plans would have to be coordinated with Earth-based teams through relay satellites, making real-time medical assistance impossible in many cases. Another area of innovation is the development of mobile science platforms that can traverse large distances and conduct multiple experiments. These mobile laboratories could include seismic sensors, magnetometers, X-ray spectrometers, and even drilling systems to access subsurface samples. To operate efficiently in the power-constrained environment of the far side, such platforms must be lightweight, modular, and capable of autonomous coordination. Swarm robotics, multiple small robots working in tandem, may become a preferred strategy for maximizing surface coverage and scientific return while minimizing risk. These systems could be deployed from a single lander and programmed to explore separate areas simultaneously, collecting data on geology, radiation, and temperature fluctuations across different sites. In parallel, innovations in launch systems and lunar descent technology are also evolving. Precision landing techniques are being refined using terrain-relative navigation, where onboard sensors match real-time images with preloaded maps to guide descent. This method was used successfully by NASA's Mars 2020 mission and may be adopted for future lunar missions to avoid dangerous terrain. Variable thrust engines, crushable landing gear, and automated hazard avoidance systems are also under development. These technologies aim to enable soft, pinpoint landings even in the rugged conditions of the far side. The potential for international collaboration is growing. As the financial and technical demands of far-side exploration increase, space agencies are beginning to pool resources. The European Space Agency, NASA, Roscosmos, and private companies like SpaceX and Blue Origin are all expressing interest in missions to the Moon's far side. Collaborative frameworks could include shared relay satellite networks, standardized docking systems, or joint science missions. The Artemis Accords, a set of principles for responsible lunar exploration led by NASA, emphasize interoperability, open data sharing, and peaceful use, setting the stage for multinational efforts to reach the far side. The technological hurdles of exploring the moon's far side are formidable but not insurmountable. Communication blackouts, extreme environmental conditions, terrain complexity, and the need for autonomous systems have challenged engineers and scientists for decades. However, with each new mission, innovative solutions are emerging. From relay satellites and AI-driven rovers to advanced power systems and autonomous sample return missions, humanity is steadily building the capability to explore, study, and one day inhabit the far side of the moon. As these technologies mature, they will not only open a new frontier on the moon, but also pave the way for deeper exploration across the solar system. The far side is no longer a mysterious void. It is becoming a proving ground for the future of space exploration. As the scientific and strategic significance of the moon's far side becomes increasingly clear, the question of how humanity governs and cooperates in this uncharted realm has become a global focal point. The far side of the moon, unlike any other region in the near-Earth space environment, presents both an unprecedented opportunity for peaceful collaboration and a potential flashpoint for geopolitical competition. Given its remote and radio-quiet conditions, this region is primed for groundbreaking science, particularly in radio astronomy and planetary geology. However, with spacefaring nations racing to establish a presence and infrastructure on the moon, including on its far side, the absence of universally accepted legal frameworks poses serious challenges. International cooperation and the development of fair governance structures have thus emerged as critical elements in the evolving narrative of lunar exploration. At the heart of the governance dilemma lies the outdated and often ignored Moon Treaty. Officially known as the Agreement Governing the Activities of States on the Moon and Other Celestial Bodies, this 1979 treaty attempted to create a framework for the peaceful and equitable use of lunar resources. It declared the Moon the common heritage of mankind and sought to prohibit ownership claims by any one nation or corporation. However, major space powers, including the United States, Russia, and China, never signed the treaty, rendering it largely ineffective. Its broad principles, while noble in intent, failed to offer actionable or enforceable guidelines for activities such as mining, permanent habitation, or military use. The lack of global consensus on its terms has created a vacuum in international space law, especially as technological advances now make lunar resource extraction and colonization feasible. As nations return to the moon, especially with more robust capabilities, new frameworks are being drafted to fill this legal and diplomatic void. The most prominent among these is the Artemis Accords, introduced by the United States alongside its Artemis program. These non-binding bilateral agreements promote transparency, peaceful exploration, data sharing, emergency assistance, and sustainable practices. They also encourage signatories to notify others of their activities, particularly when establishing so-called safety zones around lunar installations. While the accords have been endorsed by more than 30 countries, critics argue that they reflect a US-centric vision of space governance and could foster exclusionary practices. Some view the safety zone concept as a de facto territorial claim, conflicting with the spirit of the 1967 Outer Space Treaty, which prohibits national appropriation of celestial bodies. On the other side of the geopolitical spectrum, China and Russia have been crafting their own cooperative lunar agenda. In 2021, the two nations announced their plans to jointly build an International Lunar Research Station, ILRS, by the 2030s, with components potentially located on the moon's far side. While still in early development, this program represents a serious alternative to the US-led Artemis initiative. It is also a strategic declaration. Space will be a domain of long-term national interest, prestige, and influence. China, in particular,
has used its Chang'e missions to demonstrate a willingness to collaborate, offering payload slots to other countries, including Sweden, Germany and the Netherlands, on previous lunar missions. This openness suggests that, while competitive in some aspects, China is not entirely opposed to multilateral science on the Moon.
Given the Moon's finite surface and scientific value, particularly on the far side, which is geologically distinct and radio-shielded, there have been growing calls for establishing neutral science zones. These would be regions dedicated solely to peaceful, collaborative research, overseen by an international authority or consortium. One proposed example is the creation of a large-scale radio observatory on the far side, free from national branding or defense applications. The unique location would allow scientists to observe low-frequency cosmic signals undetectable on Earth due to human-made radio noise. Constructing such an observatory would require joint investments, data-sharing agreements, and carefully negotiated protocols to avoid interference between parallel missions. While the concept remains largely theoretical, it illustrates the kind of institutional imagination needed to avoid a new lunar arms race or colonial-style land grabs. The far side also offers unique opportunities for modular multinational infrastructure projects. Much like the International Space Station, future lunar bases, especially on the far side, may be best constructed through shared platforms. These could include interchangeable habitat modules, shared energy grids, and jointly operated communication systems. Such modular designs would not only reduce the financial burden on any single country, but also promote mutual interdependence and reduce the temptation to act unilaterally. In this scenario, even smaller or emerging space nations could contribute meaningful technology or services, building diplomatic capital and scientific capability in the process. Yet many hurdles remain in making such cooperative models a reality. Data transparency, for instance, is a lingering issue. While countries often publicize mission successes, they may withhold key scientific or technical data to preserve strategic advantages. The dual-use nature of many space technologies, meaning they can be used for both civilian and military purposes, complicates transparency efforts. Lunar rovers, spectrometers, and communication satellites could theoretically support weapon systems or surveillance operations. This ambiguity raises legitimate concerns among rival nations and underscores the need for strict verification and confidence-building measures. Environmental protection is another domain of emerging importance. Though the Moon has no atmosphere or life as we know it, human activity, especially on the scale envisioned by some lunar development plans, can still cause irreversible harm. Rocket exhaust plumes, mining excavation, thermal waste, and even human footprints can damage delicate regolith layers, contaminate samples, and obscure scientific baselines. To date, there are few regulations that govern such environmental impacts on the Moon. The preservation of historically significant sites, such as the Apollo landing zones or early robotic mission areas, also remains largely voluntary. As interest in the far side increases, there may be pressure to designate specific regions as protected reserves, akin to national parks on Earth. Equally urgent are questions around non-militarization. The Outer Space Treaty prohibits the placement of weapons of mass destruction in space, but it is vague on the deployment of conventional weapons or surveillance systems. Some military strategists have floated the idea of placing sensors, tracking systems, or even command nodes on the far side, taking advantage of its concealment from Earth. Such developments would likely be perceived as escalatory and could prompt tit-for-tat actions by other space powers. Codifying a robust anti-militarization regime for the Moon and ensuring that enforcement mechanisms exist will be critical for long-term peace in cislunar space. Perhaps the most contested governance issue going forward will be resource rights. As technology matures, lunar mining for water ice, rare earth elements, helium-3, and construction materials is becoming more realistic. The far side, in particular, holds untapped mineral potential in regions like the South Pole Aitken Basin. Yet who has the right to exploit these resources? Under the Outer Space Treaty, no nation can claim ownership of the Moon, but it does not explicitly ban the use or commercialization of its materials. The Artemis Accords endorse the idea of extracting and utilizing lunar resources, framing them as legally permissible under existing law. But this interpretation is not universally accepted. Without a widely ratified international agreement, mining operations on the far side could become contentious flashpoints, especially if conducted by private companies or under the flag of one nation. To address these looming issues, there have been recent calls for the creation of a Lunar Governance Charter, a kind of updated moon treaty that reflects current realities and anticipates future developments. Such a charter could establish rules for site selection, infrastructure development, environmental protection, scientific cooperation, and dispute resolution. It would ideally be managed by a neutral international body, perhaps an extension of the United Nations Office for Outer Space Affairs, UNOOSA. However, achieving consensus among the world's major space powers, each with its own priorities, red lines, and strategic calculus, will be enormously difficult. Nonetheless, there are reasons for cautious optimism. Shared scientific goals, budget constraints, and the complexity of operating on the far side may push nations toward collaboration by necessity. The early phases of lunar exploration, particularly through robotic missions and sensor networks, have already involved multinational partnerships. If properly structured, future cooperation on the far side could serve as a model for broader planetary governance, offering lessons for missions to Mars, asteroids, and beyond. The far side of the Moon is more than just a scientific frontier. It is a political and ethical test bed for how humanity manages shared resources and ambitions in space. The next few decades will likely determine whether the Moon becomes a place of unity and discovery or another theater for Earth's rivalries and disputes. The choices made today about treaties, partnerships, and principles will shape the lunar landscape for generations to come. As we stand on the brink of a new space age, the importance of clear, inclusive, and enforceable lunar governance cannot be overstated. The Moon's far side, hidden from Earth's view due to tidal locking, presents a unique and scientifically valuable environment for studying the history and evolution of not only the Moon itself, but also the broader solar system. As lunar exploration matures into a phase defined by international competition, advanced technology, and deeper scientific goals, the far side has become a focal point for a new era of discovery. The scientific payoffs from research conducted on the lunar far side extend across multiple disciplines, from planetary geology and seismology to radio astronomy and astrobiology, offering a treasure trove of knowledge that has the potential to transform our understanding of celestial mechanics, solar history, and even life itself. One of the primary scientific objectives on the far side is the investigation of the Moon's internal structure. Because the Moon does not have plate tectonics like Earth, much of its interior has remained undisturbed for billions of years. By deploying seismic instruments on the far side, scientists can measure moonquakes and seismic wave propagation, which helps construct detailed models of the Moon's internal composition. This includes delineating the boundaries of the crust, mantle, and core. Since the far side has remained largely untouched by human activity and is shielded from terrestrial electromagnetic interference, it offers a pristine environment for capturing delicate seismic signals that could otherwise be drowned out by noise on the near side. Deploying a far-side seismic network, possibly with long-lasting autonomous landers, would greatly enhance our knowledge of the Moon's geological layering, thermal profile, and tectonic quiescence. Core sampling in regions such as the South Pole Aitken Basin, one of the oldest impact sites in the solar system, is another critical endeavor. The impact that created this enormous crater likely excavated material from deep beneath the lunar surface, potentially even from the Moon's mantle. If scientists can obtain core samples from this region, they may be able to study material that dates back over 4 billion years, offering a direct glimpse into the early history of the Moon. This could also have implications for our understanding of the Earth-Moon system's shared history. The materials uncovered may be remnants of the ancient lunar crust, or even contain traces of early Earth matter ejected during massive asteroid impacts. Such findings could refine theories about the Moon's formation, particularly the giant impact hypothesis, which posits that the Moon was formed from debris resulting from a collision between the early Earth and a Mars-sized body named Theia. Radiation studies on the lunar far side also offer compelling scientific opportunities. The Moon has no atmosphere and a weak magnetic field, so its surface is constantly bombarded by cosmic rays, solar energetic particles, and other forms of high-energy radiation. Instruments placed on the far side, especially within permanently shadowed regions that never receive direct sunlight, can provide long-term data on cosmic radiation levels in an environment shielded from Earth's magnetosphere. This is critical not only for understanding the natural space environment, but also for designing radiation protection for future human habitats on the Moon and beyond. Data gathered from cosmic ray detectors, neutron spectrometers, and radiation dosimeters can inform us about the frequency and intensity of space weather events over geological timescales. In addition to passive measurements, the lunar far side can serve as an experimental test bed for biological studies. One possibility includes deploying sealed biocapsules containing microbes, plants, or small animals to evaluate how life forms respond to extreme isolation, fluctuating temperatures, radiation, and low gravity over long durations. Since the far side is free from Earth's radio noise, it minimizes potential interference in biological monitoring equipment. Such experiments could answer fundamental questions about the survivability of life in deep space and contribute to astrobiological models related to the panspermia hypothesis, which suggests that life could travel between planets via meteorites or spacecraft. Insights from these biological studies may also inform future missions to Mars or icy moons, such as Europa and Enceladus, where life could exist under extreme conditions. Perhaps one of the most promising scientific payoffs from far-side research is in the field of radio astronomy. The lunar far side is the only location in the inner solar system that is permanently shielded from Earth's radio frequency interference. This makes it an ideal site for placing low-frequency radio telescopes, which can observe frequencies below 30 MHz, a range that is largely inaccessible from Earth due to ionospheric absorption and man-made noise. A radio observatory on the far side could detect signals from the early universe, including the cosmic dark ages, the period before the formation of the first stars and galaxies. By studying the faint 21-centimeter hydrogen line from this era, scientists hope to understand the conditions that prevailed shortly after the Big Bang and track the large-scale structure of the universe as it evolved over billions of years. In addition, such observatories could detect flares from distant stars, monitor the behavior of black holes and pulsars, and search for signatures of extraterrestrial intelligence with unprecedented clarity. From a geological standpoint, the far side offers a diverse terrain composed of highlands, craters, and impact basins that differ markedly from the basaltic maria seen on the near side. By analyzing regolith, the loose soil and rock covering the surface, researchers can study variations in chemical composition, mineralogy, and isotopic ratios. These differences help scientists reconstruct the Moon's thermal and volcanic history. For example, the abundance of anorthosite in the highlands suggests an early crust formed by the flotation of plagioclase crystals in a magma ocean, a theory that could be tested more directly with in-situ measurements and returned samples. Additionally, comparing the regolith from the near and far sides allow for studies of asymmetry in solar wind exposure and micrometeoroid bombardment over time. These findings contribute to our understanding of space weathering, a set of processes that alter the optical, chemical, and magnetic properties of airless bodies in space. There is also great interest in the search for water ice on the far side, especially in the permanently shadowed craters near the lunar South Pole. These craters remain in constant darkness, and could harbor ice that has been preserved for billions of years. Such ice deposits would not only be a scientific goldmine, potentially trapping records of early solar wind, cometary material and interstellar particles, but also a valuable resource for future missions. Water could be converted into drinking water, oxygen for life support, or even rocket fuel by breaking it down into hydrogen and oxygen. However, accessing and verifying these ice deposits remains difficult due to the rugged topography and lack of sunlight, which hinders both power generation and mobility for rovers. Soil chemistry analysis plays an equally important role in unraveling the Moon's early differentiation. Understanding how elements such as silicon, aluminum, calcium and iron are distributed can reveal the conditions under which the Moon cooled and solidified. These observations support models of early magma oceans, crustal recycling, and the role of radioactive heating in lunar evolution. Advanced analytical tools, including X-ray spectrometers, gamma-ray detectors, and mass spectrometers, are expected to be deployed in future missions to precisely characterize these chemical profiles. Beyond lunar science, research conducted on the far side has implications for planetary science and comparative planetology. The Moon acts as a time capsule for the inner solar system, preserving evidence of ancient impacts that have long since eroded away on Earth. Far-side crater studies can refine impact models and help calibrate cratering rates used to date surfaces on Mars, Mercury, and other bodies. This cross-planetary perspective is essential for understanding the history of asteroid impacts and the role they may have played in both the emergence and extinction of life. The insights gained from lunar far-side research feed directly into the design and success of future deep space missions. Whether it's selecting suitable landing sites, developing life support systems, testing autonomy in harsh environments, or validating predictive models of cosmic radiation, each scientific discovery adds another layer of confidence and preparation. The far side of the Moon is more than a scientific curiosity. It is a stepping stone toward broader cosmic ambitions. As nations and private companies eye Mars and the outer solar system, the Moon's far side stands as both a proving ground and a place of profound discovery. The scientific rewards of studying the far side of the Moon are immense and multifaceted. From probing the earliest epochs of the universe to uncovering secrets buried deep beneath the lunar surface, this unexplored hemisphere is poised to become one of the most valuable real estate locations in the solar system. Far-side research is not only expanding the frontiers of science, but also shaping the future of human exploration beyond Earth orbit. As missions continue to gather momentum and international interest intensifies, the far side promises to be a beacon of knowledge, discovery, and inspiration for generations to come. The vision of establishing a permanent human presence on the far side of the Moon, once a speculative dream of science fiction, is fast becoming a realistic goal of 21st century space exploration. As space agencies and private enterprises set their sights on expanding humanity's reach into the cosmos, the Moon's far side presents a unique opportunity. Isolated from Earth's direct line of sight and thus shielded from most electromagnetic interference, the far side offers unmatched advantages for science, communication, and strategic planning. Its rugged, unspoiled terrain has never hosted human boots, making it a pristine and scientifically rich frontier that could soon host humanity's first permanent off-world base. This ambitious leap involves a convergence of technological innovation, international collaboration, and the development of entirely new infrastructure to support life and research in one of the harshest environments ever attempted for long-term habitation. The concept of permanent outposts on the Moon is not new. Even during the Apollo era, NASA scientists imagined lunar bases that could serve both civilian and military purposes. However, these early concepts were constrained by the technological limits of their time and ultimately sidelined due to geopolitical and budgetary constraints. What has changed today is not just the level of technology, but the strategic vision that sees the Moon not merely as a destination but as launchpad, a springboard for greater exploration, particularly toward Mars and beyond. The far side of the Moon in particular has gained renewed attention because of its isolation, scientific value, and potential as a long-term habitat. The idea is not simply to land, explore, and leave as with Apollo, but to create self-sustaining infrastructures capable of supporting human life for months or even years. Among the most promising strategies for ensuring long-term safety is the use of underground habitats within naturally occurring lunar lava tubes. These subsurface tunnels, formed by ancient volcanic activity, offer protection from radiation, micrometeoroid impacts, and temperature extremes. Unlike surface bases, which require extensive shielding, these caves offer a ready-made shelter that can be adapted with life support systems, lighting, and internal structures to host astronauts in relative safety. Such underground habitats are also beneficial in terms of thermal regulation. The Moon experiences drastic temperature changes, ranging from over 100 degrees Celsius in sunlight to nearly minus 170 degrees Celsius at night. The duration of a lunar night, about 14 Earth days, poses extreme challenges for heating and power supply. Subsurface bases would be buffered from these temperature swings, simplifying the energy management required to sustain life and operations. Timelines for sending humans to the Moon's far side are currently being drawn up by major players, including NASA, China's CNSA, the European Space Agency, and increasingly by private companies such as SpaceX, Blue Origin, and others. Most projections indicate a realistic possibility of launching crewed missions to the far side in the 2030s. However, these missions will not simply involve astronauts stepping out onto the surface and collecting rocks. Rather, they will be the culmination of years of robotic groundwork, literally. Before any human sets foot on the far side, robotic precursor missions will need to do the heavy lifting. These will include automated landers and rovers to survey potential base locations, analyze soil and radiation conditions, and test technologies for construction and sustainability. Among their likely tasks will be the construction of landing pads to mitigate the dust issues that can damage equipment during descent and takeoff. Building shelters and relay stations for communication will also be critical. Without a direct line of sight to Earth, any base on the far side will rely on orbital relay satellites, similar to China's successful Huaqiao satellite that enabled the Chang'e 4 mission. Relay constellations at Lagrange points or lunar orbit will be essential to ensure uninterrupted communication. One of the most groundbreaking ideas for reducing dependence on Earth-based resupply missions is the use of 3D printing technology, particularly utilizing lunar regolith as the raw material. This concept, known as in situ resource utilization (ISRU), is at the heart of plans for lunar sustainability. By developing the capability to fabricate structural elements, tools, and potentially even life support components using moon dust and rocks, the cost and risk associated with transporting materials from Earth could be significantly reduced. This would mark a crucial shift in how space infrastructure is built, transitioning from launch everything from Earth to build where you are. Energy will be a constant challenge, especially considering the long lunar nights. Several solutions are being considered. Nuclear power, in the form of small modular reactors, offers a compact and reliable source of continuous energy. NASA and the US Department of Energy are already working on such designs under the Fission Surface Power Project. Another solution is the placement of solar arrays along crater rims or elevated ridges that receive prolonged sunlight, particularly near the Moon's poles. These solar farms could charge high-capacity batteries or even beam power via microwave to areas in darkness, sustaining base operations when sunlight is unavailable. The potential scientific payoff from establishing a sustained human presence on the far side of the Moon is vast and transformative. While robotic missions have provided invaluable insights over the decades, they are limited by their programming, range, and lack of real-time adaptability. In contrast, astronauts on site bring human intuition, decision-making, and problem-solving capabilities that vastly increase the scope and depth of scientific research. When this human capability is applied specifically to the Moon's far side, a region relatively unexplored and geologically unique, the possibilities for discovery expand dramatically. One of the most compelling scientific opportunities lies in real-time geological fieldwork. Unlike Earth, the Moon has no atmosphere, plate tectonics, or active hydrological cycles that constantly erase or modify surface features. This makes the Moon, particularly its far side, a preserved record of the solar system's violent and formative past. The far side's crust is thicker and older, with more craters and fewer volcanic plains than the near side. By walking the terrain, astronauts can conduct hands-on analysis of rock layers, outcrops, and ejecta blankets from ancient impacts. They can identify which rocks are worth sampling, collect them with precision, and bring them back to laboratories on Earth. This work would help refine models of lunar evolution and shed light on processes such as crustal formation, magma differentiation, and early bombardment history. Beyond simple observation, human explorers would be able to conduct deep drilling missions. Robotic landers can only dig a few meters into the lunar surface, but humans could deploy larger equipment and boreholes hundreds of meters deep. These deep cores would reveal subsurface stratigraphy that has been untouched since the Moon's early formation. Analyzing isotopic compositions, trapped volatiles, and mineral distributions from these depths would inform scientists about the Moon's internal differentiation, past thermal activity, and potentially even the presence of water or other volatiles trapped below the regolith. This data would not only improve our understanding of the Moon's geological timeline, but also offer clues about the early conditions of Earth, since both bodies were shaped by similar processes in the same region of space. Astronauts stationed on the far side could also carry out high-resolution mapping of the terrain. While satellites and orbiters provide global imagery, their resolution and perspective are limited. Human explorers with portable sensors, drone-like aerial devices, and mobile platforms could map terrain in extreme detail, identifying subtle formations, microcraters, or layering that would be missed by orbiters. Such mapping is crucial for understanding local geology, planning future missions, and even selecting future base locations. Moreover, this data could assist in pinpointing locations where ancient ejecta from deep impacts has been preserved, offering access to the Moon's mantle or even Earth material launched into space by early planetary collisions. The scientific promise of a far-side lunar base also includes extensive biological and medical research. The Moon presents a unique environment with about 1/6 of Earth's gravity, high radiation exposure, no protective atmosphere, and prolonged cycles of light and darkness. Long-term habitation in this environment provides a rare opportunity to study how the human body adapts, or fails to adapt, to these extreme conditions. This includes understanding bone density loss, muscle atrophy, fluid redistribution, vision problems, and immune system changes. Previous studies aboard the International Space Station, ISS, have shown that microgravity causes a wide range of physiological issues, but lunar gravity is different. It's neither full gravity nor zero gravity, and the long-term effects of living in such an environment are still unknown. By observing how astronauts function on the Moon for weeks or months at a time, scientists can build a better picture of human limits in space. This data is indispensable for preparing future Mars missions. A journey to Mars will involve at least 6 months of travel each way, followed by extended stays on the surface. Astronauts will face psychological isolation, communication delays, limited supplies, and the challenge of adapting to Mars' 38% gravity. By simulating these conditions on the Moon's far side, researchers can refine countermeasures, training protocols, and life support systems. The Moon becomes a testing ground, a proving site for the tools, technologies, and techniques that will be essential for survival and productivity on Mars. Another major benefit of human presence is flexibility and adaptability. Robotic probes, no matter how sophisticated, are bound by their programming and hardware. They can only perform predefined tasks and often cannot recover from unexpected challenges. For example, a mechanical failure, navigation error, or unexpected terrain can bring a robotic mission to a halt. By contrast, humans can assess problems, apply creative solutions, and reconfigure systems on the spot. This ability to improvise is invaluable in the uncertain and high-risk environment of deep space exploration. Furthermore, astronauts can operate more than one system at a time, make complex decisions based on subtle cues, and adjust the mission plan dynamically based on findings. Additionally, astronauts can conduct experiments and maintenance on sensitive scientific instruments that require regular calibration, cleaning, or repositioning. A permanent or semi-permanent human base could include observatories, seismometers, electromagnetic sensors, and more. On the far side, shielded from Earth's radio noise, such instruments could make groundbreaking observations in radio astronomy, solar physics, and cosmic microwave background studies. Humans would be instrumental in keeping these observatories operational and adapting them over time to meet evolving scientific goals. The psychological and social dimensions of human presence should also not be overlooked. Extended lunar missions will allow researchers to study crew dynamics, mental health, communication strategies, and team cohesion in confined, isolated environments. These insights are critical for planning interplanetary missions, where small groups of astronauts must function effectively for years without resupply or real-time support. By simulating these conditions on the Moon, agencies can better understand the human factors that influence mission success. Human exploration can also inspire global interest and education in science and technology. Just as the Apollo missions inspired a generation of engineers and scientists, a new era of lunar exploration, this time on the far side, could spark renewed public enthusiasm for space exploration and encourage investment in STEM fields. The far side of the Moon, long hidden from our view, carries a sense of mystery that can capture imaginations and galvanize international cooperation. Besides science, construction and engineering research will also benefit greatly from a human-tended base. Experimentation with new materials, habitat designs, robotics integration, and closed-loop life support systems will all be easier and more effective with humans on site. These efforts may be essential not only for lunar living, but also as prototypes for Mars bases or asteroid mining outposts. A far-side base would also have strategic importance. The Moon's far side could house automated mining systems, laboratories, observatories, and potentially launch platforms for spacecraft headed deeper into the solar system. Because of its unique position, such a base could serve as a deep space staging ground, reducing the energy cost of launching missions directly from Earth's deep gravity well. This opens up the possibility of a cislunar economy, a space-based ecosystem of infrastructure, transport, and production between Earth and the Moon. One of the more visionary ideas includes the establishment of observatories on the far side, particularly for radio astronomy. Shielded from Earth's radio chatter, the far side is the quietest place in the inner solar system. A large low-frequency radio array built into the regolith could detect signals from the early universe, including the cosmic dark ages before the first stars formed. Observatories of this kind would allow humans to peer back billions of years into cosmic history, a feat currently impossible from Earth. The geopolitical significance of a far-side base also cannot be overstated. As nations race to stake their claim on lunar resources and territory, the first permanent base on the Moon's far side would represent a powerful symbol of technological and strategic capability. It could redefine space power hierarchies and prompt a new era of space diplomacy or competition. This has led to calls for international frameworks to manage lunar development, prevent militarization, and ensure that the Moon remains a peaceful domain. Nonetheless, the presence of humans on the far side would signal a new chapter in human civilization. as we move from merely visiting celestial bodies to inhabiting them. The presence of humans on the far side also comes with significant psychological and cultural implications. A base that is entirely cut off from real-time communication with Earth will need to be more autonomous, more resilient, and better prepared to make decisions independently. It will challenge the current models of mission control and ground-based support. Astronauts will essentially become pioneers, experiencing a level of isolation and responsibility that parallels the earliest explorers on Earth, with the added complexity of operating in a vacuum. Living on the far side will also create new cultural paradigms. For instance, how will time be managed in a place where Earth is never visible? What calendar will be used? What social and governance systems will evolve in a small, high-risk environment far from any terrestrial oversight? These are not mere hypotheticals, but crucial questions as we approach the era of permanent off-world living. In the long term, the Moon's far side might be more than just a scientific base or relay station. It could become a second home for humanity, a testing ground for life in space that teaches us how to survive, thrive, and build communities beyond our home planet. It may host the first lunar university, the first off-Earth greenhouse, the first interplanetary manufacturing hub, or even the first extraterrestrial children in a century to come. As nations, scientists, engineers, and dreamers push forward, the far side of the Moon is shedding its title as the dark side and emerging as a beacon of light for humanity's next giant leap. The success of a permanent human base there could represent a turning point in our species' journey, one where Earth is no longer the only cradle of life and the stars are no longer out of reach. So, as we look up at the Moon and imagine what lies beyond the familiar face we've seen since the dawn of time, we may soon know that just over that horizon, in the silence and solitude of the far side, a new chapter of human civilization has begun. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.